Hello everyone, welcome to the course of Digital Logic Design. In today's class, we are going to learn the concept of Hamming code. Hamming code. So what is an actually Hamming code? Hamming code is useful for the both error detection and error correction of error present in the received data. Error present in the received data. Okay. Let us say we have a transmitter and the data transmitted by the transmitter is received by the receiver. Okay. If there exists any error, okay, so the detection of error and the correction of error at the receiver side can be done with the help of an Hamming code or technique. Okay. Now, this particular Hamming code or technique follows a rule. So that particular condition is nothing but 2 power k greater than or equal to n plus k plus 1, where n is the number of bits in the given binary data and k is the number of parity bits. Okay. Now, let's see how to calculate this with whenever any binary data is given to find the errors or detect the errors. Okay. So let's take a problem and solve it using Hamming code. So let's take a problem. Encode the data bits 1101 into 7-bit even parity Hamming code. Okay. So if you carefully observe, the number of bits are 4. So number of bits of the given binary data n equal to 4. Okay. It is already mentioned in the question like these 4 bits into 7-bit even parity. They have mentioned that these 4 bits should be converted into an 7-bit even parity of an Hamming code. So 4 plus 3 gives us 7, right? So this is the number of bits n and this is the 3 is the number of parity bits. So this is one way to find out as they have already given in the question. Suppose, let us say they have not given this particular 7-bit. So how to find? So we need to follow the 2 power k concept. So what is the condition using Hamming technique? 2 power k greater than or equal to n plus k plus 1. Okay. So let's consider k equal to 1. So 2 power 1 greater than or equal to number of bits are 4, right? 4 plus 1 plus 1. So what 2 is greater than or equal to 6, which is a false condition. So this is how to check if there is no information given about the total number of bits to be converted. Okay. Suppose let's see the second condition. Let us say k equal to 2 now. 2 power 2 greater than or equal to 4 plus 2 plus 1. So 2 power 2 is 4 greater than or equal to 4, 5, 6, 7. 7. So the second condition is also false. Let's take k equal to 3. That means 2 power 3 greater than or equal to 4 plus 3 plus 1. 2 to 4, 4 to 8. 8 greater than or equal to 4, 5, 6, 7, 8. 8. So the condition is true. Okay. So at this particular condition, it became true, right? So the number of parity bits to be considered is 3. And the total number of bits what we have given in the question is 4. So n plus p gives us complete number of bits. So 3 plus 4 is nothing but the complete number of bits. That is nothing but 7-bit data. Okay. Now what we should do, we need to draw a box according to this particular given concept. Let's draw a box now. See. So total number of bits to be drawn is 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Now let's draw one more box. Okay. And okay, let's write the 3 bits. How many parity bits we need to consider? As k equal to 3 condition is satisfied, we need to consider 4 parity bits. Okay. So generally we have 8, 4, 2, 1 code, right? Okay. So the parity bits what we require is only 3. So we need to consider 2 power 0, 2 power 1, so 2 power 0, 2 power 1, 2 power 2, 2 power 3. Okay. So we need to consider first 3 bits, that is 1, 2, and 4. So the parity bits will be P1, P2, and P4. Okay. So what is the data given? N equal to 1101, right? So fill this data in the remaining empty boxes. 1, 1, 0, 1. Okay. Now let's see how to find out the parity bits. So in order to know the parity bits, what we need to do is we need to first write down the BCD format with respect to 0 to 7. So let's see. 8, 4, 2, 1 of 0, 1, 2, 3, 4, 5, 6, 7. Okay. So 0 is 0, 0, 0, 0. 1 is 1, 0, 0. 2 is 0, 0, 1, 0. 3 is 4 is 0, 1, 0, 0. 5 is 6 is 0, 1, 1, 0. 7 is 0, 1, 1, 1. So this is the 8421 table with respect to the BCD code. Now, we need to find out the solutions for P1, P2, and P4. Okay. Let's find out the solutions for P1. So, first, see, P1 means we need to consider this particular first P1. Okay. So, wherever the ones are there, okay, measure those numbers. See, 1 is at first position, again 1 is at third position, again 1 is at fifth position, and again 1 is at seventh position. Okay. So 1, 3, 5, 7. Okay. Similarly, for P2, consider 2. So second, third, 6, 7. Second, third, 6, 6, 7. Similarly, P4. So see here, 4, 5, 6, 7. 4, 5, 6, and 7. Okay, so these are the positions where we have ones. Now, what is the first position? Refer the table, this one. Okay, so what is the first position we have? In first position, we have P1. In third position, we have 1. In fifth position, we have 1. In seventh position, we have 1. Okay, and for P2, in second position, we have P2. Third position, we have 1. Sixth position, we have 0. Seventh position, we have 1. For P4, fourth position, we have P4. Fifth position, we have 1. Sixth position, we have 0. Seventh position, we have 1. Okay. Now, what we need to do is, in the question, they have given, encode the data bits 1101 into 7-bit even parity. Okay. So we need to see that the parity bits are even. So see here, the number of ones in the P1 is 3. So I will make this particular P1 as 1 such that the number of ones will be 4 and it becomes even. So my P1 data will be 1 such that the whole data will be becoming even numbers. Now, coming to the P2. Already the total number of ones are 2, which is nothing but even. So what I will do, I will make my P2 0 such that these numbers will be even numbers only. So my P2 is 0. Now let's take P4. Already 101, it is already even numbers. Okay. And the data, I need to make this P4 to 0 such that it will be in even number only. So my P4 data will be 0. Okay. So what is the answer? So in the P1 position, P1 position, we have 1, and P2 position, we have 0, and in third position, we have 1, and P4 position, we have 0, in fifth position, we have 1, in sixth position, we have 0, and seventh position, we have 1. So this is the answer, what we got with respect to encoding the data bits of 1101 into 7-bit even parity Hamming code. Okay. So this is how to calculate one. Suppose let's take another example where we take a bigger data and we are trying to detect the error and also correct the error using Hamming code. Okay. Let's take that example also and solve it. So let's take the example. Detect and correct errors, if any, in the following data. Okay. So there is no kind of even parity or odd parity given in this data. And they have also not mentioned any kind of total number of bits to be encoded or decoded. Okay. So what the given data is there? The given data is directly 1, 1, 0, 1, 0, 1, 0. Okay. Okay. So they have directly given the number of bits or the data, binary data, and they ask you to detect and correct the errors if any using Hamming code technique. Okay. So if this condition arises, what to do? So in Hamming code technique, we have a condition 2 power k greater than or equal to n plus k plus 1. So with this condition, let's see number of bits in the given data is 1, 2, 3, 4, 5, 6, 7. 7. Okay. So we already have n and we need to find out in which condition, okay, the parity bit satisfied. So let's take for k equal to 1, 2 power 1 greater than or equal to n is 7 plus 1 plus 1. So 2 is greater than or equal to 7, 8, 9, which is a false condition. Now k equal to 2. 2 power 2 greater than or equal to 7 plus 2 plus 1. So 4 greater than or equal to 7, 8, 9, 10, which is a false condition. K equal to 3. 2 cube greater than or equal to 7 plus 3 plus 1, which is nothing but 2 to the 4, 4 to the 8. 8 greater than or equal to 10 and 11, which is again a false condition. K equal to 4, 2 power 4, 2 to the 4, 4 to the 8, 8 to 16. 16 is greater than or equal to 7 plus 4 plus 1. 16 greater than or equal to 7, 8, 9, 10, 11, 12. Here the condition is true and is satisfied. So at which condition it has been satisfied? K equal to 4. So total number of parity bits will be 4, which is nothing but we need to consider 8, 4, 2, 1 consideration. 8, 4, 2, 1. Okay. And the parity bits will be P8, P4, P2 and P1. Okay. And total number of bits is 7, right? So P plus N, that is 4 plus 7 equal to 11. So the total number of digits or the bits what we need to consider is 11. So let's draw a box of 11 bits. Okay. So let me draw a box of 11 bits. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So what are the parity bits we have? 4 parity bits we have got, right? That is P1, P2, P4 and P8. Okay. So what is the data we have taken based on the data? See, what is the data? 110, 1010. So fill that data in the given boxes. 1, 1, 0, 1, 0, 1, 0. Okay. So this is how to fill the data. Now, as the parity bits are taken in are 4, that is 8421, consider in 8421 format. 8, 4, 2, 1 format with respect to 0 to 11. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. So for 0, it will be 0, 0, 0, 0. For 1, it will be, okay. Just write the 8421 or the BCD format of this. 3 will be 0, 0, 1, 1. 4 will be 0, 1, 0, 0. 5 will be 0, 1, 0, 1. 6 will be 0, 1, 1, 0. 7 will be 8 will be 1, 0, 0. 9 will be 1, 0, 0, 1. 10 will be 1, 0, 1, 0. 11 will be 1, 0, 1, 1. Okay. So this is the 8421 format of this 0 to 11 BCD number. Once we have written like this, what we need to do is we need to find the parity bits. So parity bits are taken as P1, P2, P4 and P8. Okay. First write down for what numbers there are all ones. So see this particular column where there are ones, okay, those numbers only to be considered. So first one is 1, 3, 5, 7, 9, 11. Okay. So for P2, there are ones at the places of 2, 3, 6, 7, 10, 11. Okay. For P4, there are ones at the place of 4, 5, 6, and 7. And for P8, there are ones at 8, 9, 10, 11. So let's verify the box and write down the numbers. At first position, there is P1. At third position, there is 1. At fifth position, there is 1. At seventh position, there is 1. At ninth position, there is 0. And 11th position, there is 0. Similarly, for P2, first position is P2. Remaining are 1, 0, 1, 1, 0. For P4, first position is P4. Remaining are 1, 0, 1. Now, for P8, first position is P8. Remaining are 0, 1, 0. Okay. Now, as there is no parity given in the question, it is not mentioning even parity or odd parity. So, by default, we need to consider even parity only. Okay. Or else there is another operation where we can do. We can perform XOR operation with the given numbers. Okay. So, let's see. See. 1 XOR 1, 0. 1 XOR 1, 1 XOR 1, 0. 0 XOR 1, 1. 1 XOR 0, 1. And 1 XOR 0 will be 1. So, P1 will be 1. By default, you can also consider the even parity directly. See here, number of ones are 3. In order to make this even parity, the P1 should be 1. So, that's why we need to mention 1 over here. Even if you do XOR operation also, the result will be same. So, P2, let us say 1 XOR 0, 1. 1 XOR 1 is 0. 0 XOR 1 is 1. 1 XOR 0 is 1. So, total number of ones are 3 in this one. So, in order to make this even parity, we need to mention 1. That is what we have got. So, either by default, you can choose even parity or you can do XOR operation to find the value. So, 1 XOR 0, 1. 1 XOR 1 is 0. Already we have 2 ones, which is nothing but even parity. So, in order to keep it even, we need to make P4 0. So, that is what we obtain. And coming to P8, 0 XOR 1 is 1. 1 XOR 0 is 1. Okay. So, the number of ones in this one is only 1. That is odd parity. But by default, we are considering even parity. So, to make this even parity, we are making this P8 as 1. That is what we achieve. So, P8, P4, P2, and P1. So we need to consider in 8421 format, that is P8 is 1, P4 is 0, P2 is 1, and P1 is 1. Okay. So if you consider 1011 in the 8421 format, which bit we are getting? 11th bit. So what is the 11th bit? In 11th bit, error exists. Okay. So once you calculate the parity bits and consider that in 8421 format, what is the BCD number of that binary value you need to check? That bit, go to the table and verify and make that particular bit as error bit. Now, in order to detect, okay, so 11th bit is the error bit, right? So 11th bit is error detected. Now, how to correct it? 11th bit is having value 0. Okay. So in order to correct it, convert 0 to 1. So that is how the error is corrected. So in the place of 0, we need to mention 1. So this is how the error is corrected. So once if you draw the table, complete table, okay, here, the P1 will be 1, P2 will be 1, third position is 1, P4 is 0, fifth position is 1, sixth position is 0, seventh position is 1, P8 is 1, ninth position is 0, 10th position is 1, and the 11th position is already, the error is corrected, which is nothing but 1. So, this is the answer, what we got after detecting and correcting the error. Got it? So, this is P1, this is P2, this is data 3, this is P4, this is data 5, this is data 6, this is data 7, this is P8, this is data 9, this is data 10, and this is data 11. 11th bit has been, error has been detected and it is corrected. So this is how the error detection and correction is done with respect to Hamming code technique.